today we're going to dig a little deeper into thermodynamics. By the end of the class, we'll get to the so-called first law of thermodynamics. But along the way, before we get there, I want to try to give you a somewhat deeper appreciation for the ideal gas law. Okay? So you just took a little quiz on it. So you know that the ideal gas, and remember this is for point particles, so they have no size and no potential energy, all kinetic. So that's what defines an ideal gas. Okay? And the result we know is that PV equals NKT. That's true for all ideal gases. All ideal gases. And what we usually mean is very dilute and not low temperature. At too low a temperature, you have other effects coming in, quantum mechanics. So it can't be too low, and it also must be dilute, okay, not too dense. We also have this other result that we got from kinetic theory. And this is valid for a monatomic. That means one atom molecule. All right? For example, helium does not bond to itself. So if you had a gas of helium atoms, that would be monatomic. Argon, another example. So the gases made up of the so-called noble gases, they're all monatomic. Other gases like oxygen, nitrogen, air, which is a mixture of that, and most other gases are not monatomic. Nevertheless, at certain temperatures, they act as monatomic. And we'll talk about how to deal with that later today. All right, but before we get on to a better appreciation of the ideal gas, I want to talk about when the ideal gas does not work and what happens for a non-ideal gas. So if we compress a gas, eventually the ideal gas law breaks down, doesn't work. There are two things missing from there. All right, so what's missing is molecules do have a size, and molecules have a generally weak, attractive interaction. So if I have a molecule here and a molecule here, they attract each other a little bit. All right? The force on one due to the other is towards the other molecule. Where does that come from? It comes from what are called dipole-dipole interactions. In other words, each molecule is electrically neutral, but the charge can be not quite uniformly distributed, and that leads to a little dipole moment. That induces a little dipole moment in the other molecule, and then there's an interaction. Turns out that interaction is weak. It's proportional to 1 over the potential energy is proportional to 1 over r, the distance between them, to the 6th power. All right, that's very weak. All right, electrostatic interactions go as 1 over r, just like gravitational interactions. But this dipole-dipole is very weak. Nevertheless, it has an effect on the gas. And what this leads to is the following result for the pressure. So the ideal gas law is changed to the following. All right? So this takes into account the attractive interaction of the particles, and this takes into account the size of the particles, right there. And if you look at the energy, whatever you had before, and we'll talk about how this could be modified. And then you have a change that goes as minus a n over v. So notice this term is extensive, proportional to n. That's the only extensive. And this is also extensive, proportional to n. And this part, n over v, is intensive. That's the density. All right, so this is the energy. This is called a van der Waals. So it's better than an ideal gas. But an ideal gas works pretty well, in fact, very well, for molecules like the molecules in the air. Right? You have to start really condensing the molecules before you can see the importance of the size and the interaction. But this will work better. These constants A and B, they depend on the kind of gas. So for helium, you'll have an A and a B. For oxygen, you'll have a different A and a different B. Turns out you can scale these equations to get something more where all these constants kind of scale out, but we won't do that here. Okay. You'll see that if you take a course in thermodynamics. All right. Now let's see if you really understand this. All right. So imagine that we don't have any attractive interaction, but the molecules have a size. So the size is the only thing that's important. And we have two gases. They're both at the same volume, same temperature. But one gas can be treated as point particles, and one gas can be treated as not point particles. It has a size. The molecules have a size. All right? And the same number of molecules in both. Which one has the higher pressure? Which has higher pressure? The ideal gas, all right, or a gas molecules have a size. Right? So they're not point particles. They have a little size. Which one has a higher pressure? Look at this equation. Which one will have a higher pressure? Well, let's do it. Everything here is the same. This doesn't count. I have a V minus MB. If I solve for P, this V minus MB goes underneath here. If it has a size, this gets smaller. The pressure is 1 over that. The pressure goes up for the particle with a size, right? So the ideal gas has a lower pressure, and the real gas has a higher pressure. Now you can think about why that is. Imagine this room full of students, and the students are dying to get out, right? So what are they going to do? They're going to push on the doors, and they're going to try and get out. Now imagine we doubled your size. So you're each twice as big, and you tried to get out. The doors are the same size. There's going to be a lot more pressure to get out. It's as simple as that. Okay, so adding size increases the pressure of the gas. All right, now let's do the same thing. What if we turn on the interaction? So the two gases have the same size, same number of particles, same volume, but one gas has an interaction, the attractive interaction, and the other does not. All right? So we want to look at, is the ideal gas have a higher pressure, no interaction, or attractive interaction? All right, so think about it. Well, the answer is, with no interaction, the pressure is up. Why is that? Well, again, I look at this, and what I do is I divide through by this, and then I bring this an squared over v squared to the other side. I get a negative there. So that means the pressure due to the interaction causes the system to have a lower pressure. A lower pressure. Well, that makes sense too. Imagine yourself in a room. You don't interact. You just go about your way, and then you try and get out the door. But now imagine there's an attraction between you, and you're each hugging each other. Okay? So you're all together more, so you don't press out as much. All right? So if you think about the walls of the container, the attraction of the molecules causes the molecules to come inside, not against the walls, but towards each other. And so the pressure on the wall goes down. All right? So higher pressure, this was for this, and a higher pressure for this. All right. Now let's see what this would mean if you actually measured the pressure of a real gas. So you have, first I'm going to draw P versus V. And this might be what the ideal gas will look like. Let's say that's the ideal gas. All right. So very low, high volumes. All right. The ideal gas should work. Now, which of these two effects are going to be important at different densities? At the highest density, the very highest density, so the lowest volume, which do you think will be more important? The attraction or the size of the particles? What's going to be more important at the highest densities? All right? So let me help you with this. I'm going to draw what the interaction actually looks like. If I draw V versus R, it turns out that it looks like this. Very high repulsion due to the size of the particles. Two particles can't get inside each other. All right? Very large repulsion here. And then we have a kind of attractive well down here. All right? So this is the weak attraction at large distances. All right? So we can see from this that at the highest densities, the volume very low, the size of the particles is most important. All right? So the size of the particles is most important. So the gas molecules have a higher pressure at the lower densities. So up here, at a given volume, we would have a higher pressure. Go like that. But then as the attraction comes in, it starts to bring it back in. And so what you have is this will go lower. It'll actually cross the ideal gas law. And then it'll come back and follow the ideal gas law. So this is what a real gas would look like. So at very low volumes, which is high density, the pressure is higher. Then at medium volumes, the pressure gets lower than the ideal gas. And then at very large volumes, they're the same. Because at very large volumes, you're out here, and the potential is essentially zero, just like the ideal gas. Low volume. Everybody see that? So if you did a simulation, you would see this. If you did measurements, you would see this. And notice you don't have to know a lot. you can actually figure this out. All right? And various people have developed various formulas to try and get this curve better. When I was in the 50s and earlier than that, there was a whole industry of people coming up with better formulas than this to try and fit the data with more and more parameters. Nowadays, people don't bother doing that. All right? You'll also see, has anyone ever seen the Handbook of Chemistry and Physics? I don't even know if they publish it anymore. It's this thick. And it's full of data for every gas you can imagine. Full of data. Now I don't think they bother with it. If it exists, it's online. All right? But they probably just have lots of fancy formulas that you can plug into. So far we spent most of our time talking about the pressure, this equation state. Now I want to spend a little more time on energy. All right? So for the van der Waals gas, the energy is decreased due to the attraction. The size of the particles does not add any energy to it because the particles just don't ever overlap. So there's no energy due to that. Now, what else can you measure? We learned that we can measure pressure, we can measure volume. We've learned about thermometers and how we can measure temperature using thermometers. What else can we measure? Well, the most important other thing is change in energy when we change the temperature. All right? And that's called the heat capacity. So this is something you want to know. C is always, the letter C is always used for this, is a little bit of energy added to the system by heating it, and delta T is the temperature. So this is energy added heating. And this is a change in temperature. So if you heat something up, you have a confined, like a glass of water, you heat it up. All right? You look at the heat capacity, the temperature will change. That's called the heat capacity. All right? Now this assumes certain things. The number of particles is the same. That's the main thing. The number of particles is the same. So this is called the heat capacity. Now, we also would like a property that does not depend on how much of the substance you have. So the heat capacity here depends on how much of the substance. So for instance, here's a container of water. It's half filled. If I put in a fixed amount of energy in it, I get a temperature change. If I filled the water up and put the same amount of energy into it, the temperature change would only be half as much because I have twice as much water. Okay, everybody see that? All right. So this heat capacity is an example of an extensive variable, right? It depends on how much of the substance you have. All right. So this is extensive. So it depends on how much substance there is, how much stuff there is. So in order to make a property that does not depend on that and just depends on the kind of substance you have, we define what's called the specific heat. These are just names. Don't try to put too much meaning into those names because they're bad names. Right? They shouldn't be called heat, for instance. Heat is complicated. It's an old thing that people weren't sure what it was. All right. So the specific heat, there are many ways. You could define it as the heat capacity divided by the number of particles. That's one way. You can define it by the heat capacity divided by the number of moles. That's another way. You can define it by the heat capacity divided by the mass that you have. Another way you can do it, this is not very common, is heat capacity divided by the volume. Okay? All right, so physicists like this, chemists like this, everybody's okay with this. And this is pretty rare. There might be a couple contexts where you might use. So when you see numbers in tables or on the web, it's probably going to be either this or this. So for example, liquid water at room temperature, let's say STP, standard temperature and pressure. So it's around room temperature. It's like room temperature. It's like room temperature. I don't know if it's exactly that. Who knows what room temperature is? Room temperature in Taiwan could be quite different than room temperature somewhere else. All right. It's roughly 300 degrees Kelvin and atmospheric pressure. All right, so here, the heat capacity, the specific heat, and I have to look this up. There it is, 4,184 joules per Kelvin, per kilogram, per Kelvin degree. All right, everybody got that? So we're using this definition here. So you might need this in some of the problems. What about for ideal gases? All right, so an ideal gas, you have to worry about how the heat, the energy, is added. Is it added at constant volume, or is it added at constant pressure? All right, so one does a bunch of experiments, and one can work this out. And what you find for a monatomic gas, you find CV equals 3/2 NK, and CP equals 5/2 NK. So this is specific heat capacity at constant volume, heat capacity at constant pressure. And depending on your units, you can also write this. All right, then the specific heats are, you can write in different ways. You can have CV is 3/2 K. All right, let me write what that is. CV over N, so that's 3/2 K. CP equals CP over N, that's 5/2 K. Or you can have CV equals CV over little n, so that's 3/2 R, or CP equals CP over n 5/2. So this is a little CP. So that's the heat capacity, and so notice CP, where this is specific heat, minus CV equals K, or the other version, CP minus CV equals R. Okay, depending on your units. All right. So this is true for a monotonic gas, but it turns out this thing here, that's true for any ideal gas. Any ideal gas. Not just monatomic. Be diatomic and be any ideal gas. That's true. And we have a name to measure the difference, namely CP over CV is called gamma. All right, so gamma has different values for different ideal gases. All right, so what is it for a monatomic gas? What is gamma for a monatomic gas? It's 5/3. All right. So as you raise the temperature for non-monatomic gases like oxygen, air, gamma changes. All right, need not be 5/3. But the difference is always K. And one can prove that. I'm not going to do it, but one can. Okay? All right, now before we leave the heat capacity, I just want to talk about the heat capacity of solids. And I'll talk about specific heat. So the specific heat of solids. All right, CV turns out to be, and it's CV that's only relevant because the volume of solids is pretty much always fixed. Solids don't change volume much. All right, so we'll only talk about this. And it's 3K. And or 3R. So that's the specific heat. It just depends on the number of molecules in your solid. That's astounding. Specific heat of this, specific heat of this, specific heat of this. It just depends on how many molecules you have. The heat capacity depends on how many molecules. But if you divide that out, it's a constant. It's the same for all solids, as long as they're three-dimensional. If you had a solid in 2 dimensions, like a surface or a film that was solid, you would replace the 3 by, guess what, 2. And if you have a solid in 1 dimension, like a line, like a polymer that was solid-like, the specific heat would be 1R or 1K. Okay? That's a pretty amazing result, but it's only true at not low temperatures. When you get to low temperatures, you got to fix that. That's also the case for water. That's also the case for the ideal gas or any gas. At low temperatures, things are different. All right? Unfortunately, you need to know quantum mechanics to figure that out, what's happening at low temperatures. So we won't be able to do that here in this course. Okay? So these results are only true at reasonably high temperatures. If you want a name, you might have heard of it. This is called the law of Dulong and Petit. I guess a couple of French guys. I don't know. All right, so they discovered this a long time ago, in the 1800s, I believe. All right. Okay. So now we know about heat capacities. We can always figure out how much energy is changed due to heating by just taking the heat capacity times delta T. All right? So that's something you will use in some calculation. All right. So we're going to start by going over the laws of thermodynamics. There's the Zeroth Law, which I guess they decided on as an afterthought. The first law, the second law, and then the third law, which is not needed too much, except at very low temperatures. All right, so what is the Zeroth Law of Thermodynamics? All right, what that says is if TA equals TB and TB equals TC, then TA equals TC. Well, that seems kind of ridiculous, right? What does that mean? What's the significance of that? In this context, we're just using temperature as a placeholder for an idea rather than the actual number. Because clearly, if TA is 100 degrees and TB is 100 degrees and TC is 100 degrees, it's obvious that TA equals TC. That's obvious. That's not what's important. What's important is if I have a system over here and it's in equilibrium, if system A is in equilibrium with system B, and then I take system B away from A and put it next to system C, so if B and C are in equilibrium, then it turns out that A and C will be in equilibrium. What does that mean? It means when I put A next to C, no energy will flow from A to C, or C to A. So what this really means is if system A is in equilibrium with B and B is in equilibrium with C, then that implies A in equilibrium with C. All right, that's the significance. That there's something special about equilibrium. Can anyone think of an example where, in some contexts, saying A equals B and B equals C or something like that does not imply A equals C? Here's an example right here. You are next to you, right? You are next to you. But you are not next to you, right? Right? There's an example. Here's another example. You love her, she loves him, but you don't necessarily love him, right? It won't happen. If A loves B and B loves C, that does not necessarily mean A loves C, right? Transitive property is not always true, but it is true for equilibrium, all right? And that's why it's significant. All right, so that's the Zeroth Law of Thermodynamics. Now, let's do the first law. All right, the first law just says the change in energy. So this is the internal energy. It's basically kinetic plus potential is equal to the amount of heat, the amount of energy going into the system due to heating or cooling, plus W. All right? And we say Q is greater than 0. That means heating. Q is less than 0. That means cooling. And this is work. Work greater than 0 is work on the substance. And W less than 0 is work by the substance. So these little words on and by are very important. You have to keep those straight. So is work being done on the substance, or is the substance doing work on the environment, or is work done by the substance? All right, so from up there, we know how to compute Q. Q is equal to C delta T if C equals a constant. So it doesn't depend on temperature. If it does depend on temperature, then Q equals C of T dt if C is not, right? So this is how you would either calculate it or measure it. If you measured it, you'd have to know the heat capacity and then how much the temperature changed. And then if heat capacity changed with temperature, you'd have to do it in steps. Okay, you have to do an integral sum. So now, so we know how to deal with Q. How do we deal with W, work? All right, so that's what we're going to do now. All right, so we get the idea of work from classical mechanics. All right, so I'm going to start out here using the definition of work from classical mechanics. All right, so if you remember from classical mechanics, the work done is F dot dr. Remember, that's the dot product. All right? So if I have an object and I do work on that object, it's the force on that object dotted into how far the object moved. All right? So if the object, if that was delta R, and that was F, that's a theta, then F dot delta R would equal F delta R cosine theta. Okay, so hopefully you remember that from classical mechanics. All right, so now we have to, but we're not interested in forces. We want to write this in terms of pressures. So we know that the pressure is the force per unit area. So this is equal to pressure times some kind of area vector dotted into dr. And we have a minus sign there. I'll talk about that minus sign in a minute. So what is this? This would be like some kind of area. So imagine I'm in a system here, and I have a wall, some kind of wall in the middle there. And this wall has an area A, and I want to know the pressure on that wall, on one side of that little area there. That's what we're getting at. All right? And we know that force is pressure times area, or pressure is force divided by area. Okay, so this A dot dr is the same as the volume. So we have a little section of volume, dr times the area. And so we get volume. Why do we have a minus sign there? The minus sign is because this formula is the force done on the object, right, due to external forces. Whereas this is the internal pressure. So that pressure is not on itself, but it's on the external world. So that's where the minus sign comes from. Okay, the pressure is internal. So this minus sign is because the pressure is on external world, rather than force on object. So this is how we compute work. All right, now a couple ways of remembering it is the following. If you increase the volume, if the pressure increases the volume, then dV is positive. P is always positive. The pressure inside is always positive in equilibrium. So that means this integral is positive and the work done is negative. Does that make sense? So if the volume of a substance increases, the work done on it is negative, which means it is doing work on the environment. Well, that's true. Right? Just think of a balloon. If the balloon expands, it's doing work on the environment. So the work done on it is negative. Right? And if you take a cylinder like this, and if I could press down on the top, right, I would decrease the volume. So dV would be negative. Negative times negative gives me positive. So if I decrease the volume, I'm doing work on the object. So I do a lot of computer simulations in my own research. And I've been doing it since I was a graduate student. Now, in the old days, kind of in the Stone Age of computers, you gave a job to the computer, and then maybe an hour or two later, if you're lucky, if you're not lucky, a few days later, you get the result. Okay? So I would get the result, and I would find in my simulations a negative pressure. So I'd simulate a bunch of molecules, and I'd get a negative pressure. And so I asked myself, why am I getting a negative pressure? That can't be. That's not real. What is going on? So in order to figure that out, I had the computer program print out where the particles were, where they were. And this is what I saw. So here's the system. All right, and this is what I saw. That's what I saw. So I went to the computer operator and I said, is there something wrong with your printer? It's not printing in the middle of the paper. And he said, so he ran it again. And he checked his printer. And he put more ink in it. He did everything he could. But no matter what, there was a hole in the middle. All right, so what was going on was this system was collapsing on itself. It was not in equilibrium. And so the pressure was indeed negative because it was not in equilibrium. The system was collapsing on itself. Right? And eventually this hole would get bigger. And then when it stopped getting bigger, then the pressure would be positive. All right? So sometimes you can actually measure a negative pressure, but that's only out of equilibrium, only if the system is in the process of collapsing. Okay? Like in a star, at certain stages of a star, the star will collapse. Okay? So the pressure due to the gas molecules is negative, and then you have other pressures pushing out to balance it. Okay. But in general, you can always assume in this course, since we're always dealing with equilibrium, P is positive. Pressure has to be positive. All right. It would be unstable The system would be unstable if the pressure is negative. It can't stay at a negative pressure. All right. Well, let's do a few exercises to see how this works. So we're going to do a bunch of examples. The first one is constant pressure, constant P, and the volume, about the simplest case you can give. All right? So what is W? So W equals minus the integral P dV from V1 to V2. But P is constant. So I can take that out of the integral. And I get minus P times V2 minus V1. All right? And that's the integral. Okay, let's see what that means in a picture. So we have P versus V. And if this is V2, and this is V1, so if we're going this way, right, so it's constant pressure from here to here, then the work done is the area under the... Now, if we're going from V1 to V2, V1 to V2, the pressure, the work done is negative. All right, so the area doesn't tell you whether it's positive or negative. You have to figure that out. If it was going this way, then the pressure would be positive. The work would be positive. So this is W is less than 0. This is W is greater than 0. Okay, everybody see that? All right. So in any problem you're given, sometimes you have to do an integral, but sometimes it's easier to just draw a graph. Hence the area under the curve. All right, let's do another example. 2, constant V. So what is the work done if the volume does not change? It would be 0, right? So in many cases, you'll have situations where the volume is not changing and there's no work done. There could be a Q, could be energy added due to heating or cooling, but there's no work done. The third one, which is very common, is isothermal ideal gas. So isothermal ideal gas. All right, so now you have to do an integral. And because many of you are just learning about it, I'll do it carefully. All right, so we have W equals minus the integral P dV from, let's say, V1 to V2. All right. So we have to solve for P in the ideal gas. Where's the ideal gas? Right up there. P is equal to NKT over V. All right? T is constant, isothermal. Constant T. N we'll assume is constant. There are some cases where it's not, like one you did for homework, but in most contexts that we do, N is constant. If you're not sure, just ask. All right, so this implies W equals minus, going from V1, V2. P is NKT over V dV. All right. Now, you should be able to do that integral. In case you don't remember how, I'll do it for you. All right, so W equals minus NKT times the log times, you can do it in steps, V1, V2, dV over V, and that's equal to minus NKT times the log of V2 minus the log of V1. And it's nice to write that as minus NKT, the log of V2 divided by V1. All right, so that's the answer. So if V2 is greater than V1, then we get a negative work, which makes sense. Again, if the volume increases, the work is negative. If V2 is less than V1, the log of a number less than 1 is negative, and so you get a positive work done. Okay? All right, our last example is the following. I'm going to just draw it on a PV diagram. So this is a typical kind of thing. All right? All right, so you have that, you have that, you have that, you have that. Call that P1, P2, V1, V2. Okay? So the work going over here, that work, W, let's give it a name, A, B, C, D. So A to B is just going to equal P1 minus P1, V1 minus V2 minus V1. Okay, just like we had before. WBC is 0. WCD is P2 times minus V1 minus V2, which equals plus P2, V2 minus V1. So the work is positive. And WDA is 0. So the total work, if you add it all up, it's not 0. It is P2 minus P1 times V2 minus V1. So that's the total work. And that work is simply the area inside there, right? P2 minus, let's say, P2 minus P1 times V2 minus V1. So it's that area, and in this case, it's negative. Okay? So that's the total work. So the total work is given by the area inside the curve, and you have to figure out whether it's positive or negative. In this case, it's negative. If we reversed all the arrows, it would be positive. All right, so now let's see if you're thinking. We went from A to B to C to D back to A. What is the total change in energy? What's that going to be? Total change in energy. Went all the way back to where it was. What's the change in energy? 0. So the total change in energy is 0, but that equals W plus Q. W is that, so that implies Q is minus W. And so that's P1 minus P2 times V2. So that's another way of computing Q, at least for the total system. If you wanted to know what Q was in each step, you'd have to know whether it's an ideal gas or what it was. You'd have to know something about the system, and then you can compute it. Now, I want to mention one last thing. There are certain quantities, E, P, V, N, T. They're examples of what are called state variables. State variables. They define the state of the system. Like I could define your state if you were in equilibrium, which unfortunately would mean you were dead, but I can define your state as being your energy, your temperature, pressure, volume, etc. That defines your state. They're not all independent. All those quantities are not all independent. Only maybe 3 are independent. Not even that sometimes. All right, so that's the state. There are other quantities that are not state variables. One is work. Another is Q, the energy added during heating or cooling. Thus, a common thing you'll hear people say is, I'm hot, I have a lot of heat in me. That makes no sense. All right? You don't have Q in you. You have energy. But Q, we reserve for changes in energy due to heating and cooling. So Q, W, they are not state variables. The others are.